you guys. So my name is Brady and this is the moving on day video for Basvic Chemistry, and the first thing we're going to do is go through the periodic table. So on your moving on day lesson you should have been given a periodic table. Can you stop this video and get that periodic table now? And also you'll want to get some crayons and things like that, because we're going to be doing a bit of colouring in of our periodic table. We're then going to talk about how to rearrange equations. There's 3 moles equations which are absolutely pivotal to the course. Most lessons you'll be using these equations. So the sooner or the earlier you can learn these and know how to use them, it'll just make lessons so much easier for you, because you'll just get it from the start rather than struggling through for the first month or two. And then we'll finish off by doing some dot and cross diagrams. And we're going to do both covalent and ionic. So to start us off, let's look at our periodic table, and we're just going to label it. So as I do things to my periodic table on the board, you just copy and do the same to yours. So first of all, we've got our periods. Now periods are the rows that go across. So our first period is this first row, which is hydrogen and helium. Now, as they're not as big a row as all the others, a lot of people miss out hydrogen and helium and kind of forget they're there, but they're not. Obviously they are a row, so my period 1 will be hydrogen and helium. Period 2 is lithium, beryllium, boron, carbon, etc. And then period 3, sodium, magnesium, aluminium and all that. And then 4, 5, 6, 7. And then going across, we have our groups. So going down, we have our groups. So across is periods and down is groups. So this is group 1, group 2. We're going to ignore this kind of divot for now. We'll come back to that in a bit. They don't really have a group number as far as we're concerned. So we're just going to skip straight from beryllium to boron. So boron, aluminium, gallium, indium, thallium, all of that lot. That is group 3. And then carbon, silicon, and all that, group 4, 5, 6, 7. And sometimes your noble gases here, neon, argon, krypton, xenon, and radon, sometimes they're called group 8, but sometimes they're also called group 0. So you can kind of call those whichever one you want. We then have our different blocks. So I'm going to use a different coloured pen now. We'll use a blue pen. So our different blocks, and now when we go and talk about orbitals and electronic structure later on, you'll understand why these blocks are called what they are. But basically, group 1 and 2, we call this the S block. So if I was to say, name me an S block element, you could say strontium, or you could say calcium. That's an S block element. All of these metals in the middle, and I've not been bothered to write out all of the elements, but all of these ones in kind of the divot, we call these the D block metals. So they're my D block. You probably know those as the transition metals. Transition metal, D block, pretty much the same. We've also got these 6 groups here, and these are called the P block. And I've not been able to fit it on my diagram because I've run out of space on the board. We've also got on your periodic table 2 very long rows, 14 elements long at the bottom, and that's called the F block. So you can label that F. We've also got, let's use a red pen for this one, something called the boron step. And the boron step separates your metals from your non-metals. So it might seem a bit weird, but actually most elements are metals. You probably think of metals as being quite rare, but in terms of number of elements, most things are metals. And we can separate our metals from our non-metals by imagining a set of stairs which boron's standing on. So here's boron, and it's standing on a set of stairs. Just like that. And anything on this side of the stairs, that is a non-metal. So carbon, phosphorus, bromine, these are all non-metals. It doesn't matter which colour you choose, but can you shade these in one colour? So I'm just going to go like this. And anything on the other side, there are metals. Again, it doesn't matter which colour you choose, but can you shade these in a different colour? I'm not going to do it on my board because it'll take ages to rub out, but shade those in a different colour. Okay, and that's our periodic table. The very last thing we're going to do, and we'll use, what shall we use? We'll use lithium as an example for this. So on your periodic table, there'll be two numbers. You'll have, if I just get one here, hopefully you can see that. You see with lithium, we've got two numbers. We've got a smaller number, so that says 3, and then a larger number at the top, which says 6.9. So 3 and 6.9. And we're just going to label what these two numbers are. So this bottom number here, the smaller number, we call this the proton number. And that tells us how many protons are in the nucleus of that element. So every single lithium atom has 3 protons in its nucleus. We've also got this top number, this is called the mass number. Sometimes it's called the nucleon number. And that tells us how many protons and neutrons added together we have. So the mass number is the protons and the neutrons. The proton number is just the protons. So if I take the difference between these numbers, that will tell me the number of neutrons. And you'll notice it might seem a bit weird, but this mass number, the proton number, is always a whole number. Because you can only have a certain whole number of protons. You can't have half a proton. But your mass number, it can be a decimal place. And that's because this mass number is an average of lots of different mass numbers. And we're going to talk a lot more about that when you do your first week of lessons. But just don't, for the moment, don't be confused that it's a decimal place. It's not that you have 0.9 of a neutron. It's just it's an average of lots of different numbers. Okay? So that's our periodic table. That's how we label it. And definitely you're going to want to keep hold of this now you've made it. You'll be wanting to bring that to every single lesson. We use it almost every single lesson, so definitely have that at either the front or the back of your folder. A little thing about folders as well, you're going to want to keep your notes nice and safe. At GCSE, what can tend to happen is you make notes, you put it in your exercise book, and then kind of fling it over your shoulder, and it goes in a pile in your room. That's not going to work at A-level. It's completely different. You have to be constantly going back and looking over your notes from lesson. We make a lot more notes than you would at GCSE as well. So you're going to want to keep these in a nice, safe place. So a proper ring binder folder is what you need, not just like a plastic wallet or a little booklet, a proper ring binder. And every time you do a page, you can take it out and stick it in that booklet and keep it nice and safe, dated with a title, so you can find it easily if you think, actually, I've forgotten about the periodic table, I need to go back and look at that, and it's all there for you. So, bear with me 2 seconds whilst I rub this off, and then we'll talk about rearranging equations. Okay, so there are 3 main equations you need to know for chemistry, and they are moles equals mass over AR. The symbol for this, the symbol for moles is just N, the symbol for mass is M, and AR just has a symbol AR. AR is the relative atomic mass. It's basically the mass number from the periodic table. Now, yeah, we'll just leave it as that for now. The second one we need to know is moles equals volume times concentration, and the symbols for that would be N equals capital V small c. And the third one we need to know, and we will be going through these a lot in lessons, this is just a quick introduction to get you ahead of the game when you start. The third one we need to know is moles equals the volume of a gas divided by the number 24. And again, we'll go into a lot of detail about why that is in a bit. So that symbol would be N equals V gas over 24. This equation, really weirdly, only works if you're dealing with a gas. If you've got a liquid or a solid, it won't work. So that's why it's volume of a gas. This one could be the volume of a solid, it could be volume of whatever. So here's our 3 equations. We'll start with this first one there, and we'll just talk about how we can rearrange that. So in maths, and this is the key to rearranging, in maths you can do whatever you want to an equation as long as you do the same thing to both sides of the equation. So let's just rewrite this a little bit bigger. So I've got moles equals mass over AR. Now, let's say I want to get mass equals. So I'm going to rearrange this to get mass equals. What I need to do is figure out how I can cancel out all of my other terms on this side. So I've not got mass equals, I've got mass divided by AR equals. So this AR is kind of getting in my way. So what I'm going to do is I'm going to multiply both sides by AR. So I'm going to multiply my left-hand side by AR, so AR times moles, and I'm going to multiply my right-hand side by AR. Now that's going to put the AR on the top. But what happens now is the AR on the top cancels with the AR on the bottom. So I've got mass equals, and then mass equals AR times moles. If you're good at maths, what you can do is, if this is on the bottom, you can kind of just drag it to the top of the other side. That's basically how it works. But the way you're doing that is by multiplying both sides by AR and then cancelling. So look at another one. Let's do two more. So let's say we've got moles equals volume times concentration. And let's say I want to get volume equals. So look at this side, I want it to be volume equals. What else have I got? I've also got concentration on this side, so I need to get rid of this concentration. So what I'm going to do is I'm going to divide both sides by concentration. So divide my left-hand side and divide my right-hand side. These two are going to now cancel, so I can get rid of them. I've got volume equals moles divided by concentration. Again, if you're good at maths, all I'm really doing is taking this concentration and sticking it underneath the other side as a divided by. I'll do one final one. Let's do a moles equals volume of a gas divided by 24. If I want, again, volume of a gas equals, then I've got this extra 24. I don't want that. I want that to be gotten rid of. So I'm going to multiply both sides by 24. Those two are going to cancel. So one on the top, one on the bottom. Volume of a gas equals 24 times moles. Okay? So that's how we rearrange. I say you can do it with any equation, but those are the three most important equations to learn in chemistry. And then very, very finally, we'll just talk about how to do dot and cross diagrams. So first of all, we've got these magic numbers. And the magic numbers, if you was to go anywhere in the world and you was to say to a chemist, what are the magic numbers? Then the chemist would say 288. And it's how many electrons can fit inside these first three shells. So if I have a nucleus, inside my first orbital here, or shell, I'm going to have 2 electrons. Inside the second can fit 8. And then in the third can fit another 8. And when you draw them, draw your electrons in pairs, because it makes it easier for you to count how many are in there. If I just drew a circle and I just do that, it becomes a lot harder for me to count how many I've done, and then it sounds silly, but you will miscount and you'll end up drawing 7 or 9. If you do it in pairs, 2, 4, 6, 8, it's nice and easy to see. Also, electrons do tend to travel in pairs as well, so it's actually quite a realistic way of drawing them. So, 288, they're my magic numbers. You can figure out how many electrons will be in the outer shell of an element by looking at the periodic table and looking at the proton number. So the proton number tells me how many protons are in the nucleus, as we said earlier. But in an atom, and this only works for atoms, not ions, but if we're just dealing with atoms, then the number of protons in the nucleus will equal the number of electrons that are surrounding that nucleus. So let's do lithium again. Lithium has a proton number of 3, so it has 3 protons in its nucleus and 3 electrons around the outside. So remembering 288, I'm just going to do lithium has got 2 in its first shell, and it must have 1 in its outer shell. And the whole purpose in life of any element is to become stable. That's what they want to do. They want to become more stable. An element becomes stable by gaining a full outer shell of electrons. So when we're drawing these dot and cross diagrams, what we're trying to do is give our elements full outer shells. That's their aim, that's what they want to do. So let's look at some covalent molecules first. So covalent molecules is when we have two non-metals. Now, you'll know if your elements are a metal or a non-metal by looking at your periodic table and looking at that boron step and seeing which side of the boron step your elements are on. So the first one we'll do is CH4. So if you was asked to draw a dot and cross diagram of CH4, this is what I would do. Well, first of all, I'd think about the electronic configuration, so 2A8, of all of my elements. So let's start with carbon, because that's the central atom. So carbon's got 6 electrons, so that means it's going to have 2 in its first shell, so 2 crosses, and that means it's going to have 4 in its second shell. So, well, I won't draw them on yet, but it has got 4 electrons there. So I'm thinking carbon's got 4 electrons in its outer shell, so it needs 8 to have a full outer shell. So 4 to 8, that means it needs 4 more electrons. And basically, an element with covalent bonding anyway, a non-metal will gain an electron by making a bond. And each time an element makes a bond, it gains 1 extra electron, actually shares an extra electron. So the fact that carbon has got 4 electrons, that tells me it needs 4 more, so that tells me that carbon will make 4 bonds. And as carbon always has 4 electrons, what it turns out is carbon always makes 4 bonds. So you can tell how many bonds an element will make just by looking at how many more electrons it needs. So what I'm actually going to do is I'm not going to draw these electrons as pairs, I'm going to draw them separately. Because with covalent bonding, the way my elements share their electrons is by overlapping their orbital. So just over here, I'm going to draw hydrogen. Hydrogen's only got 1 electron. And as this is a dot and cross diagram, not a cross and cross, I'm going to draw that as a little circle, like that. So what happens when my 2 non-metals come together via covalent bonding, their orbitals overlap. So I'm going to overlap my hydrogen orbital with my carbon, and then each of them shares an electron with each other. And I show that just by keeping the electron in between the 2 orbitals. So here's carbon's donation, and here's the electron of hydrogen, this one there. So they're now sharing that electron. So remember the magic numbers, 2, 8, 8. So hydrogen has 1 electron. It needs 2 to be happy, because this is its first shell, so it will make 1 bond. Look, it's making 1 bond. Carbon, we said, has 4 electrons. It needs 4 more to be happy, so it'll make 4 bonds. And that's why the formula is CH4 and not CH, because each hydrogen can make 1 bond, and carbon needs 4 bonds, so it bonds with 4 hydrogens. So all I would do is add all the others on the same. Don't forget to keep it as a dot and cross diagram, not a cross and cross or a dot and dot. So separately. And that would be my dot and cross diagram for CH4 methane. Okay, just do one more, then we'll move on to ionic. And we'll do CO2. So CO2, again, carbon's my central atom. So I've got my 2 electrons in the first shell. And again, it's got 4 electrons in the second shell, so that means my carbon needs to make a total of 4 bonds. But if I draw oxygen, oxygen has got 8 electrons, so it's going to have 2 in its first shell, and then 3, 4, 5, 6, 7, 8. So 6 in its outer shell. So each of my oxygens needs to make 2 bonds. So you can see now why the formula is CO2. Because carbon needs to make 4, and each oxygen needs to make 2. So that means we've got the right number of bonds. So if each oxygen needs to make 2, that means we must be making a double bond. Now remember, a single bond is where each element shares 1 electron. So a double bond must be where each element shares 2 electrons. It's just the same thing twice. So I'm going to draw 2 of my carbon's electrons here, and 2 on the other side. I'm then going to overlap my oxygen, just like before. So here's its 2 inner shell, and I'm going to have 2 electrons there. And remember, oxygen's got 8 electrons in total. So 1, 2, 3, 4, and then these 2 unbonded pairs. We call these lone pairs of electrons are going to go on the outside. And I'm going to do the same on the other side. 1, 2, 3, 4, 5, 6, 7, 8. And as long as all my electrons are shared in between the 2 orbitals there, it doesn't matter how I arrange them. So here I've just put them next to each other, whereas there I put them on top. It doesn't matter as long as they're between the 2 orbitals, that's what counts. Okay. So that's covalent bonding. We've also got, finally, do ionic bonding. And ionic is between one metal and one non-metal. Okay? So with ionic bonding, it's not as nice as covalent. Ionic is between a metal and non-metal, and they don't share their electrons by overlapping, they steal them. And what always happens, is your non-metal steals electrons from your metal. So let's say, for example, I have NaCl. Now, I'm not going to draw all the inner shells now. All I'm going to draw is the outermost shell, because that's actually the important one. The inner shells don't do too much in my diagram. It's just the outer one. So if I draw just the outer shells only, then sodium will have 1 electron in its outer shell. And just drawing the outer shells, chlorine will have 7 electrons. And you can see now this is a lot quicker and easier to do. And actually, in most exams, they wouldn't expect you to draw the inner shells, just the outer shell, just because it takes too long, especially if you've got a big element with like 5 shells. So what's going to happen here? Well, my non-metal is going to steal electrons from my metal. So they all want a full outer shell. So this electron here is lost, so I can get rid of that. And it's given, it's not given, it's stolen by the chlorine. Don't forget to keep it as a cross. This doesn't change into a dot. I need to keep it as a cross to show the examiner you know that this electron came from the sodium. Okay? So this is now happy, it's got 8 electrons. Sodium's lost its outer shell, so if you imagine the next shell down will be full, sodium's actually got 11 electrons, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I only drew this shell, but now I've removed that electron, you can see the next shell is full. So sodium's full, that's happy. Chlorine's full, that's happy, but I've missed something out. This wouldn't get me a mark in the exam because I've not put the charges on. The charge of an electron is -1. So imagine this pen has a negative charge. That could be my electron. If I pick up the pen, I have picked up the negative charge, so I now have a negative charge. So this chlorine, it's picked up the electron, so I need to put it in square brackets and show it's got a negative charge just by putting a minus there. With the sodium, that has lost an electron, so it's lost a negative. If you lose a negative, you become positive. So I'll get a little plus there. And that's it, that's my final diagram. And you can just leave this like that. If you want, you can just leave the empty orbital, that's fine, but I don't see the point in that, you may as well not bother. So I don't generally bother doing that. Okay, we'll just do one more. We'll do magnesium oxide, so MgO. So again, if you look at your periodic table and do the electronic configuration, you'll see magnesium has 2 electrons in its outer shell. And you'll see oxygen has 6 electrons in its outer shell. Okay, and don't forget, this is a dot and cross diagram, not a cross and cross, or not a dot and dot. So in order to be happy, magnesium needs to lose 2 electrons. And in order to be happy, quite conveniently, oxygen needs to gain 2 electrons. So what's going to happen is my oxygen is going to steal the 2 electrons from the magnesium. And they're going to stay as crosses, and they're going to go there. So now my magnesium has lost 2 electrons, so it's lost 2 negatives, so that will give it a 2+ charge. And you do need to put the number before the sign. That sounds really picky, but if you said +2, that actually means something else in chemistry. So don't do that, always put the number first. And my oxygen has gained 2 electrons, so that will now be 2- there. So that's how to use the periodic table, that's how to rearrange the 3 most important equations, and that's a little bit of practice at covalent ionic bonding. If you could try and do that sheet we gave you now, I think it was quite a long one, but you have got the summer to do it. If you're not sure about how to do a question, maybe just have a flick back through this video, the answer might be there, or you can always look it up online. Or if you know somebody who's very good at chemistry, you can ask them. Okay? With all homeworks on chemistry, we do expect you to complete every question. So if there's a question you can't do, just leaving it out is the worst thing in the world, and you'll not succeed in the course if you do that. You need to be spending most of your time on the questions you can't do and figuring out how to do them. Okay, so that's another big difference between GCSE and A-level. You're supposed to be much more of an independent learner now. So you need to take it upon yourself to find out the answers to questions you don't know. Don't just stick it to one side. If you do that, all this work you don't know is just going to build up and build up and build up, and it's going to get to Christmas time, and the pile's going to be so high, there's nothing you're going to be able to do about it, and it'll fall on you, and it'll be too much. So you really need to keep on top of the work. That's one of the biggest keys to success at A-level. Stay on top of the work. Make sure each week you are confident you know how to do every bit of work. That's your aim. And if you don't know how to do it when you start at college, come and see one of us. We've got loads of online videos, loads of online worksheets to help you. You've got your textbook, your your notes from lesson. So there's lots of places out there to help you. We've got a Facebook page, so you can ask a question on that and we can get back to you. You've got all the support you need, but it's up to you now as an AS student to come and get that help, to get that support. Okay? And that's one of the biggest differences. So I will see you, have a good summer holidays, and I will hopefully see you in a couple of weeks.